All right, so we're at the very last carboxylic acid derivative for this chapter, the nitriles. And just like we've done with the other ones, I want to start out with preparation of nitriles, and then we'll go into the reactivity. And we've actually seen a little bit of the preparation of nitriles in first term. And the way we can do this is via an SN2 reaction. So what I mean by that is, let's say we have some sort of alkyl halide, or at least something with a good leaving group, and we treat this with something like sodium cyanide, right? So in this case, the carbon has a negative charge. It can do an SN2 reaction, can kick off our leaving group, and by doing this, we do an SN2 reaction, and we can get this new nitrile group installed. In fact, we've also installed an additional carbon, which is kind of neat. So the main thing to be aware of when you're doing these reactions is you have to use a starting material that has a relatively unhindered backside, meaning it's best if this is methyl or primary. If it's something like a tertiary carbon, we're not going to get SN2 chemistry to occur, and we can't make our nitrile. All right, the second method is from amides. And this is one of the reactions I showed you on your reaction map during that amide video, but we really didn't get into much detail. And what I said was, if you have an amide, you can treat it with thionyl chloride, that's SOCl2, and by doing that, you can create a nitrile. In addition, you're going to make SO2 gas, that's sulfur dioxide, and HCl as your byproduct. So let's take a look at this mechanism. And the mechanism is a little bit different than most of the mechanisms we've seen using thionyl chloride, but there are some similarities. So if you remember, thionyl chloride is a really, really good electrophile. So it's seeking out electrons, and in this case, the lone pair electrons on oxygen can attack the sulfur and kick up electrons onto that oxygen. So what we get is this kind of funky looking intermediate where we form a bond to sulfur. The oxygen has a negative charge, and you've got two chlorines here and here. And one thing I did forget is the reason that oxygen's so reactive is this nitrogen can dump down electron density up to that oxygen, making that lone pair a pretty good nucleophile. In fact, when you do this, the most common intermediate that you see is the intermediate where you have this nitrogen with the positive charge, because the nitrogen's happier having the positive charge than this oxygen up here. All right. So in the next step, what we want to do is we want to kick off this chlorine as a leaving group. So this chlorine right here is going to kind of get kicked off as a leaving group, and we'll get to our next intermediate. We still have this carbon-nitrogen double bond. That nitrogen still has a positive charge. Let me fix this R here. We still have this bond to oxygen, but now the sulfur's got a double bond to oxygen, and we still have one chlorine left over. The chloride that was kicked off is going to float around in solution, and I'm just going to go ahead and scoot everything down a little bit. All right, so we've got this intermediate now. What we'll do next is deprotonate. So we'll just write minus H+, and we'll get rid of that proton off of the nitrogen. That means that we've got something almost resembling an imine at this point. And we, in this next step, can use a really weak base. In this case, it's probably even just going to be chloride to do this final deprotonation step. And so what the chloride's going to do is it's going to grab that proton. It's going to clamp down. It's going to clamp down here and then further kick off the chlorine. Now, if you remember, all of the previous times that we used thionyl chloride, this group right here becomes sulfur dioxide. So that's the driving force of this reaction. We normally don't think of chloride as being a very strong base, but in this case, it's good enough. So we can go ahead and we can show this new triple bond to our nitrogen. We've got HCl as our byproduct, and then the sulfur dioxide gas is going to bubble out of solution. So this is a kind of clever way of making a nitrile directly from an amide. All right, so now let's jump into the reactions of nitriles. I can't talk. The reactions of nitriles. And there's a few reactions that are covered in the textbook, so we're going to focus on those. The first one is one we actually saw already in a problem of the day. And that's where if you treat a nitrile with dilute acid and heat, what you'll do is you'll quickly interconvert this to an amide. And then once you're at the amide, you can continue pushing all the way to a carboxylic acid and your ammonium ion. So I'm not going to go over the full mechanism because it's pretty steppy, and it's similar to all of the mechanisms we've seen already. But if you are struggling with it, just email me and we can maybe set up a review session on this. All right? And then a second way of accomplishing this is by treating this with sodium hydroxide and heat, followed by acid. So this would be the base mechanism rather than the acidic mechanism shown above. So just like with amides, these will work under either conditions, and we can push it all the way back to the carboxylic acid. All right, the next one I wanted to show you is with Grignard reagents. So let's make a note here that this is hydrolysis. And then the next one is going to be with a Grignard reagent. All right, and this one's a little bit different. We're normally not used to seeing Grignard reagents reacting with the nitriles, or with nitriles, but in fact they do, and we'll see why. So let's say we've got this Grignard reagent. This can attack, let me change my colors here, the carbon, just like it would a carbon in a CO double bond, and then kick electrons to that nitrogen. All right, and when we do this, what we're going to get is a carbon-nitrogen double bond. We'll get that second R group installed, but now this nitrogen will have two lone pairs and a negative charge. Oftentimes students will say, well, can a Grignard attack in again? Not exactly. If that were to happen again, let's just even draw this out. You don't need to include this in your notes. What would happen is we'd have to kick electrons up to nitrogen again, giving it a 2 negative charge. That's just too unstable and it will not occur. So it'll stop at this point. And then in the next step, what we'll do is we'll treat this with some sort of weak acid or even water. So in this case, we can just treat this with water. And we can get a functional group that looks pretty familiar. If you remember from the previous chapter, this is just an imine. So to get to our final product, all we need to do is continue this reaction with excess water and catalytic acid. And by doing that, we can interconvert our imine to our ketone, which is pretty neat. So I'm not going to go through and show this whole hydrolysis of imines to ketones because we went over that in a previous chapter. But it is kind of neat that we can go directly to a ketone from a nitrile by using a Grignard reagent. In fact, I should include the R prime symbol here. All right, the last one I wanted to cover are reductions. And luckily, the reduction reactions are pretty similar to what we saw with amides. And you need a strong reducing agent for this reduction. So we're going to use LAH in excess, followed by an aqueous workup. And when we do this, we're going to get a new amine. The one mistake I see a lot of students make is they forget to include this carbon here. So remember, we're not losing a carbon during this reaction. The carbon's staying put. we're reducing that triple bond all the way to a single bond and getting to the amine. All right, so let's finish up by quickly drawing our reaction map. And then what we'll do tomorrow is we'll start working on synthesis practice. Okay, so for this reaction map, I'm going to have my nitrile right here. I'm going to have some sort of alkyl halide up here. I'll have an amide down here. I'll put my carboxylic acid over here. I'll put my ketone on this side, and then I'll put my amine down here. So like we saw, we can go from an alkyl halide to a nitrile by treating this with sodium cyanide, but this all depends on this R group being unhindered, right? Because this is an SN2 reaction. If we want to go from an amide to a nitrile, that's when we use thionyl chloride, that's SOCl2. And those are the two primary ways through which we can make our nitrile. Now, if we want to react our nitrile, we can convert it to a carboxylic acid by using a lot of water, acid, and heat. And we can also do this using base, but it's a two-step reaction. We need NaOH and heat, followed by acid. And remember, that acid step is just to ensure that that proton's hanging on at the very end. If we want to go to a ketone, that's when we use our Grignard reagent and we make our imine. And then in our second step, we can hydrolyze that imine all the way to our ketone by using H3O+. And we typically do this with a huge excess of water to push that imine all the way to the ketone. All right. And then last but not least, if we want to reduce our nitrile to an amine, we can use something like lithium aluminum hydride in excess, followed by an aqueous workup. All right, so that's where we'll stop right now. Like I said, tomorrow we'll come back and we'll work on a bunch of synthesis problems because I know there's a huge amount of reactions to keep track of in this chapter.